I think a major advantage this theory has over establishment is they don't actually have an explanation for why evolved stars should have giant iron nickel alloy cores. Now, that would have to do strictly with both nucleation inside of iron nickel vapor and grain growth. So you have an initial substrate and then you have nucleation, probably homogeneous nucleation, which means the same throughout, which then condenses onto the interior, forming the core as the star evolves. And three basic concepts I want to overview right now is you have a boundary, you have nucleation, which is the beginning where the initial substrate is layering, and then you have grain growth where it repeats and the grains get bigger and bigger and bigger. So right here you have your boundary, and you have nucleation, which is that thin part right next to it. And then you have grain growth where the grains get bigger and bigger and bigger. And you can see that inside of geodes as well. Quartz geodes, where you look on the interior, you have the initial nucleation on the outside of the geode, and when you go inwards, the grain growth gets bigger and bigger and bigger. So that's a good example of what happens. Only with stellar evolution, it happens not on the outside in, it happens on the inside out, because that core deposits very, very slowly outwards, kind of like a pearl being layered. And I'm on this Wikipedia page, grain growth. It says here, grain growth is the increase of grains, crystallites, in a material at high temperature. Well, high temperature, obviously, the interior of a star is pretty damn hot. This occurs when recovery and recrystallization are complete, and further reduction in the internal energy can only be achieved by reducing the total area of grain boundary. The term is commonly used in metallurgy, but is also used in reference to ceramics and minerals. So it has here the rules of grain growth. And one of the rules is grain growth occurs by the movement of grain boundaries and not by coalescence like water droplets. So you have your grain boundary changing, and then more grains grow where that boundary had changed, so it grows outwards like that. That's why when you see amethyst, it's like all crazy like this. And another rule is the boundary movement is discontinuous and the direction of motion may change suddenly. Now, when it comes to forming the core of an ancient star, it may change suddenly, yes, but for the most part, the iron and nickel stay put in the center. There's no changing direction to where the core grows like a giant tube or like a pyramid, or the main structure it forms is a spherical iron nickel core, because that is where all the material is centered. That's where the majority of the gravitation is, or that's the direction gravitation allows for this giant crystal grain to grow. And another point, I clicked on crystallite. Now, crystallites are very common. You see them a lot. I don't know if I can pull this page up for you, you can see it. But you have malleable iron, electrical steel, solar cells, galvanized surfaces, zinc, and various other structures. That might be too bright for you guys. Let's let the phone adjust. But you see all different types of crystallites on there. It says here polycrystalline or multicrystalline materials, or polycrystals, are solids that are composed of many crystallites of varying size and orientation. Crystallites are also referred to as grains. And we also can see grain growth inside of the Thomson structures, which exist inside of meteorites. And as we all know, meteorites are the interiors of ancient dead stars. It's what the interior of the Earth looks like. Mercury, Venus, that iron-nickel alloy, that's what's present inside those interiors. They are small, even microscopic crystals that form during the cooling of many materials. Their orientation can be random, with no preferred direction, called random texture, or directed, possibly due to growth and processing conditions. Fiber texture is an example of the latter. The areas where crystallite grains meet are known as grain boundaries. Most inorganic solids are polycrystalline, including all common metals, many ceramics, rocks, and ice. The extent to which a solid is crystalline has important effects on its physical properties. Sulfur, while usually polycrystalline, might also occur in allotropic forms with completely different properties. Although crystallites are referred to as grains, powder grains are different. They can be composed of smaller polycrystalline grains themselves. So basically, what we have here is, if we can actually understand that the iron catastrophe that establishment accepts as sound science is not only false, but it doesn't actually explain anything in terms of what's actually found. If you're going to form something that massive, and the iron core of the Earth, iron nickel core of the Earth is pretty damn massive. If you take the diameter of Texas going this way, multiply it by 2, that is the radius of the core. And it's a spherical structure, meaning it's solid throughout. It's not 2D like Texas is, it's 3D. It's a thick ball of iron nickel sitting in the center of the Earth. It's a very, very, very large ball of iron nickel. And the only way to form something like that is to have a previously very, very, very hot, violent thing existing, which has all that material already in its vapor form. Where do we see those types of objects in the universe? Well, they're called stars. That's where all the vapor iron nickel is. And when the star loses a lot of mass, all that iron nickel can collect in the center, undergo homogeneous nucleation, and then start growing crystals and form a giant crystal core. But we won't see this kind of understanding inside of establishment, which is why I have to go ahead and direct people to actual science versus the iron catastrophe, which is just made up because they didn't know what they were doing at the time. But there you go. I would suggest looking up all this stuff, crystalline structures, polycrystalline, amorphous structures, and look up things like X-ray diffraction and how to figure out how the crystals are shaped, how they're formed, and study rocks and minerals and crystals. Like, look at them. Like, look at geodes. Notice how everything forms in a geode. Notice how the grain growth changes and the colors of the geode changes as the grain growth, the rate changes as which it deposits and that kind of stuff. There's a lot to learn from the world around us, Don't just assume these astrophysicists know what they're talking about, because they just don't. Especially with regards to actually explaining what happens to the star and its internal structure. They think by sending up $1 billion telescope, they're going to find the secrets of the universe. No, the secrets of the universe are right below your feet. Today is December 7th, 2015. Hopefully this helps people out a little bit.